see an overview of the internals of an optimizing compiler. The first thing that happens is that the source code file is examined 1 byte at a time in order to find so-called tokens. This is called lexical analysis. For instance, it should recognize operators, identifiers, numbers, and similar things, and keywords, of course. Okay, then this sequence of tokens is checked to see if it is correct according to the grammar of the language. That's syntactic analysis. And then semantic analysis. Does this make sense? For instance, are all variables declared before they are used when the language requires that? This course is not about this. That's for a normal compiler course. And you will not have any disadvantage for not having read or taken a normal compiler course before this. Anyway, the output from this analysis is an abstract syntax tree. What is that? Well, it's a tree in which unnecessary details are abstracted away. Okay, so let's see an example. If we have this source code, well, there is not much to abstract away, but if we add a semicolon here, then it will not be in the abstract syntax tree. So this is the source code, which the lexical analysis and parser analyze, and then this tree is constructed during the syntax analysis. This tree is then checked for semantic errors. To check that it is correct according to the language, to the extent that it is possible to check that. For instance, if it's a divide by 0, it's usually not possible to check it at compile time. So this is the abstract syntax tree, and this is also the input to the code generator, which generates something called 3-address code, which we see here. And our course is concerned about things like this. Sequences of code which looks like assembler code, but at the symbolic level. So the operands are typically variables. In this case, the code generator walks this tree, and when it comes here, it says it wants the value of B and the value of C, and it will add them using this instruction. Put it in a temporary variable, sometimes used with the $sign, and then it's copied to A. You might wonder why we do not put A at once here. Well, it simplifies the compiler to do it like this. So the input to the labs, etc., is sequences like this. Okay, let's go back. So when we have this abstract syntax tree, it's translated to the 3-address code that we saw. And after that, we either do optimization or produce assembler code or machine code directly. For instance, in my compiler, I do not produce assembler code. Assembler code, that's a textual representation of machine code. But I skip that because it's not needed. It's easier to go from 3-address code directly to the machine code. Okay, so if we now use optimization, the first thing to analyze is of course, to see which functions are in the source code. Okay, and then for each function, we do something called control flow analysis. And what we do is to create a directed graph, and the edges describe the branches. We will see that in a moment. Well, we can see it at once actually. So if we have this source code, there will be one node for this, and then there is a branch to either this or to that. Okay, and then after each of these, there will be a branch to this one. And one of the branches can be avoided, of course. Okay, so when we have analyzed this, we do initial optimizations, such as constant propagation. Constant propagation means expanding constants and putting them where they can be used. We will see that later. When we have done constant propagation, we may, for instance, know the bounds of a for loop. I mean the lower bound and the upper bound. And that makes sense because that we want to know that, because then it's easier to do so-called high-order transformations, which analyzes and optimizes loops. What's the purpose of that? It is to vectorize, and that is simmed vectorization, and parallelize. That means running the loop, different iterations on different cores. And also to do locality analysis, locality optimization. That is to optimize the usage of the cache memories. After that, we do scalar optimizations. Recall scalar optimizations involves optimizing code where the operands is a variable which can be put in a register, in a normal register. Then we do instruction scheduling, instruction selection, which means mapping from this 3-address code into machine instructions. And then schedule this to optimize the pipeline usage, and then do register allocation. At this point, we can actually keep the 3-address code, but just note which kind of instruction it is. So we don't have to produce a completely different format. We can wait with that.